Hello everyone and welcome to homework 3 for computational methods. In this homework we're going to be talking about mixtures and molar flow rates, fractions, and compositions of those mixtures. Okay, so let's get started. So oftentimes in chemical engineering, you're dealing with flows of a mixture. And usually you don't actually know the mole fractions, but you need to know them. So when you're solving for them in a problem, you usually need to, set them in some sort of nonlinear equations, a bunch of equations like that. And when you try to solve those equations, you have to set constraints. So for example, these molar fractions, they have to be positive and they have to be less than 1, aka the values have to be from 0 to 1, and the sum of them all those x sub i's, they all have to equal 1. So right there, that's what, 2 inequality constraints per component plus an extra one for the summation. So for this simple problem that has only 3, that'd be 7 constraints you'd have to apply for the problem. And the more constraints you have, the more difficult the problem can be. So what my professor came up with was a variable transformation, shown here. I'm sure everyone can see it. Shown here, where you transform each molar flow rate in terms of these v sub i's. Now these v sub i's, they are unconstrained. They can be any number from negative infinity to infinity. And when you solve for them, and when you have all the v sub i's and you solve for them, you can get x sub i's that fulfill the constraints of being between 0 and 1. And when you do it, having the second equation here, which is 1 minus the sum of all your x sub i's equals the last one, that fulfills the last constraint of them all having to equal a sum. Okay. Now, how exactly would we solve for this sort of thing? So if we have these, well, if we wanted to input some VIs, how would we input them? So let me take a quick snip of these. And I have here a OneNote for me to derive these. Okay, so there's our equations. Right here. So what does that look like in practice? So let's say we have our 3-component mixture. So we have 3 x sub i's and a total flow rate. Well, solving these equations, that would come up with 2 v sub i's. Excuse me, 2 v sub i's that we'd have to solve. So what would the equations for each x sub I look like? Well, we have x1 equals to e v1 divided by 1 plus e v1 plus e v2. Now x2, let's separate these with a semicolon. X sub 2 equals a similar equation with e v2, and they'd have the same denominator. So that'd be 1 plus, that's bad, let's try that again. 1 plus EV1 plus EV2. And the third one, let me move this over a little bit. Oops. Now our third composition is simply 1 minus x1 minus x2. So that'll fulfill our last constraint of them all having to equal 1. Okay. So we have these three equations, and we want to solve for v sub 1 and v sub 2, right? So what we want to do first is we want to take this equation here. Let's just start with x sub 1, because that'll make it easier. Start with x sub 1. We're going to take that equation. Actually, no. Let's use this general form. So using this general form here, we're going to take that general form and we're going to raise both sides to the natural, or not raise, we take the natural logarithm of both sides. So we have the natural log x sub I equals the natural log of e to the vi divided by 1 plus ev1 plus ev2. These are on that. Okay. So now using the laws of logarithms, we can separate this term here into the natural log of vi minus the natural log of 1 plus ev1 plus ev2. Okay. So now we're here. This term becomes vi. And so if we solve for vi, what we end up getting is we have v sub I equals natural log of x sub I plus the natural log of 1 plus ev1 plus ev2. Okay, so now that we're here, what we want to do is we want to take these terms here, make it blue. We want to take these two terms here and substitute them in terms of x1 and x2. So how are we going to do that? Well, let's give these a variable, let's call it u. Okay? Now these two together, well, we'll use that in a second. So you see how up here we have x1 and x2, ev1 over this denominator, and x2 is ev2 over the same denominator. What we can do is when we add them together, the denominators stay the same, so we can safely add the numerators. So we get a term like x1 plus x2 actually, let me do that in a different color. Let's do You'll see why in a sec. So let's do x1 plus x2. And when we add them together, we can just safely add the numerators because the denominators are the same. So we get EV1 plus EV2 over 1 plus EV1 plus EV2. Okay. So as you'll notice, this term here that I called U repeats up here and down here. So if this is U, and this is U, then we can actually do that quick substitution, and then we can rearrange this equation a little bit easier. So we're going to call x1 plus x2, we're going to call that z. So rewriting this gives us z equals u over 1 plus u. And we're going to solve for u, so we can substitute in here. So we have z plus z times u equals u. And we have z equals 1 minus z times u. So once we move this term over, distribute out the u's. So then that leaves us with u equals z over 1 minus z. Okay, so then we can use this. We can use this transformation to put into here. See, let me just show you what that equals. So we get u equals x1 x1 plus x2 over 1 minus x1 minus x2. Careful to distribute this negative over. Okay, so then we can plug that in here. So we get v sub I equals the natural log x sub I plus the natural log of 1 plus this term, x1 plus x2 over 1 minus x1 minus x2. Okay, so we have this. And this, honestly, is our expression for v sub I. This is all we need, and we can go ahead and test some values for x sub I and see how that affects our v sub I and vice versa. So let's go here. Let's do that. So let's make a quick function that, gives, if we give it three compositions, it'll give us our v1 and v2, right? So v1 equals, shoot that me, snip over this general form. No. Okay. So we got this general form. And as you can see, if we solve for v1, we have v1 equals np dot log. And this log term, this log here is base e. So we got log of x1 plus np dot log of 1 plus, then we have x1 plus x2 plus z parentheses divided by 1 minus x1 minus x2. So, yeah. Okay. So now for v2, it's the exact same equation. Just change that to a 2. Change that to a 2. And we'll return v1 and v2. Okay. So as you'll notice in this function, we don't actually use x3. And that's because x3 gets calculated by that second equation that was shown in homework, where it's just 1 minus the sum of the rest of the molar fractions. So let's run. Let's give it the problems with the initial ones we were given. So 0.1, 0.4, and 0.5. 0.1, 0.4, and 0.5. Oh, commas are good. Bingo. So this quickly calculated our v1 and our v2 values right here. So that just goes to show that, yes, they can be negative. Heck, they can even be greater than 1 or less than negative 1. So let's try another one. Let's do 0.6, 0.3, and 0.1. There we go. Now both of these v values are greater than 1. See, 1.7 and 1.8